Good evening. Welcome, everyone. Thank you for joining us for Apollo 2.5 Meetup at Silicon Valley. We are very excited today to tell you the latest innovations of Apollo Open Platform, to show you new algorithms, new vehicle, and to live demonstrate new tools for you. And more importantly, how the developers and the partners around the world, like you, use Apollo Open Platform to jumpstart their own autonomous driving projects. Autonomous driving is once-in-a-century technology that will change the world for better in a significant way. It will have profound social and economic benefit in long term. And with open platform, we can change the world together for better and safer. Let me give you a quick overview of Apollo. We started Apollo officially in July last year. We released Apollo 1.0 July 5th. And we keep our promise and keep fast iteration. In September, we released Apollo 1.5. In January this year, at Las Vegas, we released Apollo 2.0, a big milestone for Apollo to enable day and night autonomous driving for simple urban roads. And we just released Apollo 2.5, which we'll give a deep dive today to show the latest algorithms, the new scenarios, and the new tools we develop to Apollo 2.5. Apollo get tremendous momentum since very beginning, thanks to all the developers and the partners around the world. With their positive support, Apollo became the most vibrant open autonomous driving platform in the world today. Over 9,000 developers recommend Apollo in GitHub, and over 2,000 developers using Apollo code, and over 100 company partners and with active commercial development plans. And up to today, over 200,000 of lines of code open sourced in GitHub. And without the developer support, Apollo cannot become today. And so next, I will show you several examples how the developers use Apollo to do their own autonomous driving projects. Richard is from our neighbors, from Nevada University. And Richard told us they use Apollo source code to their own projects in Nevada University. They said with high quality open source code, Richard can focus on the key questions of autonomous driving. So it significantly increase the productivity of their small team. They don't have reinvented the wheels. It really shows how Apollo is really open capability and share resources to push the innovation forward. This is a developer from China, and they use Apollo to build a very simple agriculture autonomous driving project. As you can see the screen, it's very simple and bare minimum. And when we developed Apollo at the beginning, we never thought our Apollo can run in such simple configuration. But that is really the power of open platform. They said they did encounter a lot of questions during this porting, but they get support from the open community. It's the power of the open platform. Not only that, and we did a test ride on Apollo, public test ride. So here in Sunnyvale office and also in China, with Apollo 2.0, the capability of autonomous driving in simple urban roads. There are more than thousands of test drivers already tested on this one for our media friends, for our partners, and for the Apollo developers, and 99% positive rating. And after one media friends take on this ride, they said Apollo is really zipping the traffic and stop gracefully at the traffic light and turn on the signal light, very precise. So next, I would like to show you a small video clip to see how Apollo is really running in cars and during night. I think what you, I think what you see here, and indeed the car is in the backside. You can see the car right there, and all the code and the hardware configurations you can get from our GitHub. So include the UI interface. So everything you see in the video, you can get it in our GitHub. Is that amazing? Thank you. And after we released Apollo 2.0, we did hear the developers' feedback. They say they want more scenarios. And the data installed on the sensor is still expensive. They want lower the entry barrier to use a low-cost configuration. And they want have more vehicles support. And they also want, is there any new tools and make the innovation faster and the developer easier? So we hear you. And the developers are really our best moving forward force. So we hear all of them. So today, we are really too happy to present Apollo 2.5, which has more scenarios that a vision-based perception, has lower barrier, real-time relative map, has more powerful tools. We will have live demonstration of dream view on stage. And more vehicles, we will have our partners, autonomous staff, to show how they put Apollo into their new vehicle. Indeed, it's also in the back. So I think Apollo 2.5 is really big milestone for us. And I would encourage everyone to start get to know and learn that. And there is 3 steps to get familiar with Apollo. The first one is attend the Apollo Meetup. What you did today, that's very good. And the second step, after attend the Meetup, you can go to our website, GitHub/Apollo Auto, to download our code, to fork our code, to start using in your own project, to see how good it is. And the third step, we really like your feedback, just like previous feedback, tell you what will improve and how we can make Apollo better. So I think with all the support, with all the partners and the developers, we can change the world for a better and significant way. So next, I will introduce our colleague, architecture of Apollo perception, Tae Eun, to talk more about vision-based perception. Please welcome Tae Eun.
Thank you, Jingao. Thank you for coming. My name is Tae Eun Choe. Currently, I'm leading perception team at Baidu USA. Today, I'll talk about vision-based perception for autonomous driving. Up to Apollo 2.0, we mostly used LiDAR as a main sensor, and camera was mostly for the traffic light detection. Now we added more function in cameras to make the car drive only with the camera. So here I'm comparing LiDAR and camera. So LiDAR is active sensor, as you know, laser beam and then coming out, then they can determine all the 3D the object. And camera is a passive sensor. So LiDAR provides a really accurate 3D estimation of the environment and the dynamic objects. Also really good tool for the localization using the HD map. However, we have a certain problem with the LiDAR, which is a shorter range. The range of the LiDAR is shorter compared to camera. So usually the manufacturer says they can see up to 250 meters, but actually when we are using it, we can see like 60 meters, something like that. And also the reliability. Physically, it's quite hard to keep it reliable, mostly because of the physical sensor moving around. So we are waiting for the solid state LiDAR. But however, most of the product which can see further is the moving part, and then we are not sure how long it can go. And also the main problem to make the LiDAR as a main sensor for the mass production is the price. It's really expensive right now. So we are waiting for the cheaper sensor to use LiDAR more often. And also the technically main problem is it's prone to fail under the rain or snow. So when there's a raindrop, the laser reflect, or especially when there's a puddle on the ground, it provides all incorrect estimation of the object. So that's the main problem of LiDAR. However, Waymo, Cruise Automation, Baidu also, and most of the other companies are using LiDAR as a main sensor. Controlling camera is relatively better in weather. If you have a chance to drive the Tesla car, you could see that under the rain, it can drive pretty well, only using the camera. Also, the price is pretty cheaper. This is the main reason to use the camera. And also, it can see much further. So you can see, I can say up to 120 meters, it can see pretty well. Also, it has a main problem, which is at night, it cannot see well, especially for localization. You have to see surrounding, but only you can see is the lights. Or you need the active sensor. For your car, you have a headlight, so you can see the front part, but side or back, you don't have if you don't have any the lights, you cannot see any environment. So that's the main problem of using camera for localization. Currently, Mobileye, Tesla, or other startups are using camera as a main sensor. Here, I'm listing the sensors from little bit relatively cheaper to the more expensive one and see what's their functionality in autonomous driving. Radar is pretty good sensor for the longitudinal distance measure. It can see pretty far away, reliably on 120 meter. And also, the velocity measurement is really accurate. Ultrasonic can be used for the very slow traffic, like a highway bumper to bumper situation. It can be used for the AEB in very close distance, or can be used for the vertical or parallel the auto parking. And the GPS and IMU is really useful sensor, most for the localization. We can get coarse localization output, but when you have a really accurate one, you can get really fine output from there. So it's GPS and IMU is critical sensor to use for the autonomous driving. And Here we have frontal cameras, either one or two or three, which helps a lot for the longitudinal control and also lateral control. And when you see the landmarks in the scene, it can be used for the localization. When you want to change the lane, then side cameras are required or side radars. So lane change or turns or for the localization, actually for the localization, when you have a side camera, you can get more accurate the localization. And side radars can be substitute of the cameras for the lane change and turns. It's a different story, but we can use internal camera for the either infotainment. You can do some gesture to control the infotainment system, or that camera can monitor the driver if they are sleeping or doing something else, or they can check occupancy of the drivers. And also, of course, when we have a LiDAR, it provides a really good localization and provide a good estimation of the surrounding area. Here I listed some functions from relatively cheaper function to complicated one, and we'll see which sensor we require. So the first thing is the audio and the video warnings. So it's a safest way of providing the information to driver, and also pretty useful. Even we have a full autonomy, if they provide a certain audio or graphical warnings, it's very useful. So for the collision warning or lane departure, it's all useful with the audio warnings. Also, they can provide a traffic light, current traffic light changes or traffic sign information when drivers are driving. And next thing is the longitudinal control, or autonomous emergency brake, or autonomous or adaptive cruise control, ACC. For this function, I'm claiming we need at least the radar, front radar and front camera. Front radar is really good to detect the object in distance, and also camera is good to detect all the objects in the scene. However, the camera has an issue with the pitch when car is moving around. The distance measure could be incorrect. So the radar can help that. And also front radar's problem is cannot detect stationary vehicle well. So in that case, camera can supplementarily used. And another typical part is actually quite difficult problem is auto steering. I'm talking here at lane keeping and tailgating. Stay on the lane or follow the front vehicle. For that, we need the same sensor for this task, but we need a really accurate the lane estimation. Another function is the lane change. So either automatic lane change or the human provide the command and then it can be changed, or overtaking. So for this function, we need a side cameras or any side sensors. And also automatic turn to make a turn either by the human or automatically. We need those side sensors and front radar and all the sensors above. So actually when we can do turns, left turn, right turn, and exit and at the highway, almost the L4 is done. Level 4 autonomous driving are done. However, we have certain issues like weather or day or night. All those cases, to cover those cases, we need all the sensors and then should cover all surroundings. The goal of Apollo 2.5 is the low-cost autonomous driving. We want to drive highway, which means we need really fast processing in perception, and also can see far away. We try to drive without map, or we introduce a relative map. And this method will not stop at traffic light or traffic sign, which means it's a level 3 or level 2. And we'll do the ACC and lane keeping as a main function. Here's a block diagram of the vision-based autonomous driving. We have image and the radar sensor output coming out, and we do the pre-processing, gain control, tone mapping, or demosaicing. When it's done, those images are fed to the deep network module. Here, currently, what we are doing is lane detection and object detection. We'll do two tasks for 2.5. So when we have those objects detected, then we convert in post-processing side to 3D space. At the 3D space, we track them, and we can measure the distance, velocity, or time to collision, and we combine with the radar. After the fusion, we can provide a final output to planning and control side. For the lane output will be mostly used for the lane keeping, but it can be also used for the pose estimation, and we can use that using the IMU and the lane output as a 3D geometry measurement for the pose estimation of vehicle. Then they can be used for all the geometry of 3D side. And finally, we make the final output to generate the lane detection output. Image processing, pre-processing. So in camera side, there's an exposure control and gain control. Rather than let the automatic method do it, if the software can handle that, that's the best case. Especially for exposure, traffic light detection need a certain exposure control. And for the currently in 2.5, we are not introduced this one, but we already have it in 2.0. And gain control, when we're at nighttime or facing sun, gain control is a key function for the reliable image capture. And tone mapping is really important for the high dynamic range imagery, especially at night or when there's a shadow on the ground or when camera is facing sun. The tone mapping is a key technique. And also, we are mostly using Bayer pattern of the camera, so we need some demosaicing or filtering techniques. So when we are done with the image post-processing, it will fed to the deep network. This is the core part of the machine, the perception. And currently, we are detecting object and lane. And we can train individually and then get the output, which provides actually the best performance. But problem is it takes time and need more sensors to do that. And synchronization of object and lane is also takes time. So inevitably, we have to use co-train. Co-train means we extract the object and lane at the same time. So for the base network, we use the darknet, the YOLO detector. So we use their own network for the object detection and added a certain attribute on top of that. And we have another the segmentation layer in deconvolution layer for the lane detection. For the real-time process, not only doing the co-training, we change the float parameters to int 8. We currently use the TensorRT, and we could get 13 milliscan per frame, which is 76 frame per second using NVIDIA 1080 Ti. So I'll talk about object detection and lane detection. First, object detection. For every single object, the images, we detect the object. For each object, they have a certain attribute, which is the types, car, pedestrian, or bike. And we'll have a 2D bounding box as output. And also, each object has an orientation in 3D. And each object has a 3D size. For this, we use the LiDAR output for the actual 3D size. And for the far object, when LiDAR cannot see, we use just the standard size for the 3D size of the object. When we have this output, we further post-processed to acquire 3D position of the object and velocity also in vehicle coordinate. And also, we track those objects to provide a persistent track ID for each object. Here's a block diagram of the object detection and tracking. So this detector is the DIM network. It provides either object detection output here or lane the segmentation output. After the object detection, we convert those 2D object to 3D. This is the changing 2D to 3D. And from the previous object IDs, we track them and then we filter their movement and then provide the final the object distance and also ID. So this is the object detection and tracking algorithm. I go into deeper. So 2D and 3D converter. So we have a 2D detection output, and we have a heading, and also the 3D shape of that. So if we just put it on top of that, actually it does not match well. So to fix that problem, we had to do some post-processing, which is binary search of the object. We have object and move around until it converges to the location in 2D bounding box, or we stop when after the maximum iteration. I'm sorry for the thin lines, but this is the actual output, so it's quite difficult to see. But when we have a 2D bounding box detection like this, and we have a center position, and when we put the 3D bounding box, then it looks like this, which is totally off. So 2D to 3D converter search around this area. Actually, you have this offset, so actually directly jump to here and search again, and then eventually find that this is actually the best 2D, 3D matching on this 2D bounding box. So we got this correct backside and the front side also, and it's all happened to the other object also. We did it in the KIDI data set, and it also worked pretty well as long as you have the correct camera parameters. So we have a tracker called the cascaded tracker pipeline. So when there's tracks from the previous frames, we have all the track IDs. Now, from the current frame, we have object detections. We have to assign those ID to the new detection, or if the detection is a new one, we have to assign new ID. So this one provided this concept. So when we have all the detection, we compare with all the detection, previous track ID and current detection. And first fit tracker is using 2D bounding box size and also 2D position. After that, we have another tracker using the deep learning feature as a similarity measure and then provide the similarities. And third level is using canalized correlation filter, which takes time, but it provides more accurate tracking information. So all those, the relationship between the previous one and current detection, we have affinity metrics providing all the similarity measure of them, and we represented in affinity metrics. Among them, we use the Hungarian algorithm to assign the best matches. After that, when there's a matches, they are all assigned to the new ID, and we track the older record, or we assign new ID for the new detection. Here's the cascaded track pipeline. We are using the affinity metrics as a representation, and when we have enough time, we can use all the trackers. But if we don't have enough time, we can just use the 2D bounding box position, and that's good enough. But if we want really good tracker, when there's a lot of traffic and then we want to detect that, if that's the goal, we can use that. So speed of the vehicle is determined by the processing time. When we go slowly, we can learn this tracker all the time. But if we are going really fast, then we don't have much time for the tracker, then we should use just one or two trackers and then provide output, because we have a limited time. If we cannot process the frame fast enough, then it cannot detect, and then PNC will, planning and control may judge incorrectly. So that all those design is depending on the real-time process. Next, the main task we are doing is lane detection and tracking. Lane is very important for the lane keeping and also determine the object in front of you. So we detect the lane line up to 120 meters if there's no object in front of you. And also we assign left lane and right lane, which determine our ego lane, and also determine find the next left lane, on also another next lane, and also 3 other lanes in the right side also. Currently, we can categorize to broken lane line or solid lane line. We are not supporting to classify double, yellow, white, or butt dots, but we plan to do that. When we have a lane line detection in current frame, we can do tracking similar to the object tracker, but it's a much simpler problem because they are much similar and then they are static objects. So we can track them across multiple frames. Here's the example of the scene. The cameras, usually for the 2.5, what we are suggesting is put the horizon to the center of the image, and then, so this is the center of the image as a horizon, then that means the pitch angle is 0. Also, you hope, so this horizon is also same as the half of the image, which means your roll is 0. And also the pitch, whenever you go, if it's always stay on the center of this position, then yaw is 0. So we set all 3 angles to 0 as a recommendation. But even though it's a little bit off, that's all fine. But you need a calibration. Currently, we are using the LiDAR as a reference to calibrate the cameras. So we have this image. And after going through the deep network, we have this the probabilistic map, heat map of the detection. And currently we use just 0.5 for the threshold value to binarize this image output, which is look like this. So this is the binary image of the lane line. So main task is we have to assign this one as a L0 left lane, right lane, and next right lane, and another right lane, also next left lane. We have to do that. For that, we have to find these gaps and then connect all together. It's cumbersome, and actually, people may not agree on this, but lane line is very important for the localization. So those small points tell a lot about their local position in longitudinal distance. And also this feature is really important when you are doing pose estimation. So we are keeping it currently for the lane mark, but of course we plan to do the whole lane line detection later. So this is the output of the network, and we overlaid on the image, then it looked like this. So the output is pretty good, but it's mostly trained on the other countries, so it's hard actually. Sometimes when you change the country or other data, it's a problem. It's all the overfitting of the data, so you need a lot of data from all the country to make it work. So from the binarized image, we do the connected component analysis. Hopefully you can catch up with all those computer vision terms, but that means when there's a point, we try to find the connected component and then group them. When we have this output, we find some corners on the bounding box and find some major axis of the lane line. It can be curved or any direction, but we find this major axis, and then we can find the left inner or outer part of the lane line. Currently, we use the inner lane line for the lateral control, so we just use the inner part of the lane line. This is just a line, so sorry. So after that, we cut down the certain part of the object and then put more points. So this is straight road, so even 2 points is good enough. But if it's curved, we need a more point to represent those lane lines. So we cut down and then eventually find out all the points in there. So when we have a point, now the next step is finding this segment and that this line segment should be connected. So this is the overlaid output. And we have a camera matrix, so we convert those detection to the world coordinate. Because it's a ground, we assume that this is the planar world, so we use the homography to put all the 2D images to 3D coordinate. Actually, it's not a good camera parameters. As you can see, it's a little bit, converging. But the goal is try to connect this one and this one and this one too also. For that, we determine what's the end point of the lane line. Either there's multiple points or sometimes there's only 2 points. And using the distance between one line segment to another or the angle of those vectors, we can determine that they are close or not. So first, we try to find all the candidates. Actually, there's not many candidates because if the angle is too much, then actually they are all filtered out. But as long as we have a certain candidate, there's several connections. From here to here, they can be connected also. And then we use the greedy algorithm, Prim's algorithm for the spanning tree to find the association between one line segment to another. So this is the final output of the lane line association. And from those points, now those points are all connected and considered as a same lane line. Then we do the either cubic or quadratic polynomial fitting to provide the final lane line output. And then from there, we check this distance in C0 of the polynomial to determine either it's a left lane or right lane or the other lanes. So this is the lane line detection. And when we are doing this over the frame, then we can actually track them and then assign all the correct lane lines. CIPV. CIPV stands for closest impact vehicle. And it's the most important object on autonomous driving, which is in front of your car, on your lane. But the problem, so how we can get is we have a two lane line detection and object detection. As long as if they're object and they are closest from our scene, then they are the CIPV. The problem happens when we have only one lane line or no lane line. In that case, if we have a two lane lines, of course, we can definitely detect that. Or if we have a one lane line, we have a predefined width, and so we make a pseudo lane line and then find if there's an object or not. Also, if there's no lane line, then we can detect based on our trajectory. But currently, we assume that it's always straight and detecting it in front of you. By doing that, we have a CIPV and the lane line. Then actually, all the lateral control and longitudinal control is possible. So as I said, problem of using image alone is that the distance measure is difficult. We have to estimate the pitch angle all the time, which is quite cumbersome and difficult. But there's another substitute, which is using the radar. Radar provides really accurate distance measure. So currently, we are using one frontal camera and one the radar. We represent everything in the ego car system, which is the origin is the center of the rear axle, and this is the direct, and the other axis is the direction of the vehicle. And we learned the utility of the sensors. It'll be same for the either using LiDAR or anything, but we have a ground truth of the each detection, and we have a sensor output, and we try to find which sensor works best in certain position. We realized that the camera works well in both in lateral and longitudinal in closed area because we got output from the LiDAR. However, when it's going above our LiDAR range, then the distance measure was incorrect. However, radar provides a really good estimation, but it's good, but when it comes to the stationary vehicle or other things, radar didn't work. So the main task is we have to combine our detection from radar and camera, and if they are matching or not. After that, we have to determine what's the best location of those objects. So that's all done and sensor fusion. So it's the same thing for the LiDAR or anything, but actually the actual algorithm is already in 2.0. Here's the output of the detection. I'm sorry for this visualization, but yeah, this is the 3D, the top-down view of the object, the output. So this is our car, and red lane line shows the left lane, and blue is the right lane line. This is the next right lane line. So from here, as you can see, we have the yellow, the lane mark detection from the network. They are associated and providing this longer lane line. And this, the red color shows the CIPV among all the objects. So actually here we have a pretty bad detection because it was in different place, and it's quite confusing for the detector to do that. But this is all the overfitting of the network problem. We are keep improving this network and solve those problems. But right now we use the very small number of data to run these images. And here you can see that we have a 2-lane line, which is the broken. And here you can see the solid lane line and then 2 broken lane line. And we have a 3 detection outputs. So we can tell that laterally we are on the most right side of 3rd lane line. And also we can tell that what's the object here. So it can see up to more than 120 meters right now. Currently, we did co-directed feeding, so at the curve, it's a little bit awkward over there. But of course, we can use the cubic feeding, but problem is always use the higher polynomial. It has a tend to have a more overfitting in polynomial feeding. Here it shows the 3D the bounding box, which is useful. So when there's a vehicle here, if we have just a 2D bounding box and the next lane, it has a big bounding box like this, then they can be considered as a CIPV. Then car will suddenly stop, especially when there's a bus or truck, then car can stop. So, however, as long as we have a 3D bounding box, then we don't have to worry about those cases because the bounding box will cut down to look like this. So this is the main reason to use 3D bounding box. Maybe, sorry. I could run longer, but yeah, I just passed that. In summary, we have a solution for the low-cost autonomous driving. Of course, there's a long way to go, but provide most of the algorithm. And the main part we have is having more data and training. We use the 1 camera and 1 radar as a main sensor, and we could achieve 76 frames per second by co-training and also the into-8 network. Also, we have our own 2D to 3D converter and lane post-processing module and CIPV algorithm. We also have a really nice sensor fusion to provide more accurate estimation of the object. Thank you very much. I'll be around, so I'll take questions after all presentation is done. So for now, so I will introduce EPA for the real-time relative map. Thank you.